Alright, so let's talk about creating content for geometry-based rendering. Now, just like with the frame-based rendering, we have this problem where we know how to render these things, but we need the actual content. And just like with the frame-based rendering, we can model by hand, which is what you've been doing in class. And then, as you can tell, it looks probably unprofessional. It's really hard, and it's not an effective way to work. The other approach, of course, is motion capture. Motion capture is really cool. I've had the opportunity to work with motion capture myself, and it's a very, very standardized now technique that we use. Now, just like with the previous example in the with rotoscoping in the frame-based animation, the goal here is to leverage real people and real actors and get them just to act out like they normally would, and use that as input into our digital system. So real people, real actors, okay, and they use real objects. It's all real, and we just record what it looks like. So let me just flip over to my slides, and let's take a look at this. So notice on the one frame you have the people moving, and the other frame you're going to have what it looks like when the person's motions are linked to the...
I had one that works, which I sure as hell don't. What makes you think I'd just give it to you? Huh? Yeah, sure, Joel, go ahead. Take my card. Take all my food, too, while you're at it.
By the looks of it, you could lose some of that food.
You listen to me, you little shit.
So you see here, the person's moving like a real actor. They're into it. They're using a voice acting, and then it just links it to here. If you look closely, you'll see a series of cameras around the whole room. These are called motion capture cameras, and these actually look like Vicon cameras, which is a brand name, and they're really cool. Let's see if I can get a closer up view of one. Yeah, these little red rings around them. Let's mute this. Yeah, let's get a scene where you can see a camera a little better. Here we go. So there's a little red ring, and what this red ring does is it emits infrared light into the scene. So it floods the whole room with infrared light. Now, we cannot see infrared light. It doesn't hurt us. We just can't see it. But it reflects off of these balls and these pieces of tape. So the silver balls here. These are retroreflective, which means they reflect light back in the exact direction they came from. So it's easy for the cameras to see. So these cameras, now, they reflect off the light as a nice... it emits this light. It reflects back, comes into the camera, and then they use that information to reconstruct the 3D scene. Now I'm going to zoom ahead, and there's a better scene somewhere where you can see all the cameras. So so there's these huge arrays of cameras. Now what's really cool about this problem is it's the opposite problem of computer vision. In computer vision, opposite problem of computer graphics. In computer graphics, you have a 3D scene that we know the 3D information of. We have that information. But I wanted to generate the raster image on the sensor. I wanted to generate the raster image rather than the image plane. We have the opposite problem here. We don't know the 3D scene, except we have 1, 2, 3, 4 here, probably 30, 40 different views on the scene, where we have the image plane, we have the raster. We need to figure out what the 3D scene was. So instead of taking your matrices and going from 3D flattened to 2D, you start with 2D and you work backwards into 3D, and you overlap the data from the images to solve where those 3D things are. And this is an assignment. I've done this with a computer vision class assignment I did. It's not easy, but it's really fun. So this is a motion capture system. They're very expensive. If these are indeed Vicon cameras, when I worked with them, they're worth about $10,000 to $15,000 each. So my installation I worked with was about a $200,000 installation. Going back 10 years, this would be a multi-million-dollar installation. Okay, so motion capture is really powerful because we just capture all that data. There are variants, of course. These are markers on a face, so we can get really down to the muscle motion on a face and link that back to the 3D model, and that's a really hard problem to do as well. Of course, there are markerless tracking systems now, but I would think that in industry it's still standard to have the markers, just because it's become standard. People know how to work with it, and it's really robust once you get it up and running. Cool. So we get this motion capture. One of the problems with motion capture is you end up with a lot of data. I'm going to underline that. A lot of data, okay? In fact, when I worked with my system, it was well over 300 frames a second, 300 hertz. And the reason we do this are many. One is noise reduction. This is a noisy process. You miss frames, you lose a marker, it jitters out, there's a reflection somewhere, it jitters out of place. And so if you go 300 frames a second, we have a lot of room to average over that, or to delete erratic frames and still have a good amount of data that we can work with at the end. So if we want to get it down to 60 frames a second, we have a lot of room to delete erratic data. And another big problem related to this is keyframe extraction. Right? If I have a 20-minute scene at 300 hertz, okay, per second, that's 20 minutes times 60 minutes, 60 seconds per minute times 300 frames a second. That's a lot. That's 2 times 6 is 12 times 3 is 36,000. That's a lot of frames. Now, if you're in a video game, you don't need that. You're not going to use that. So what you want to do is you reduce this to a series of minimal keyframes, and you interpolate between them using something like lerp, and see how much you can get away with to reduce the data without seeing an impact on the quality of the result. Now, of course, if you're doing a movie, a high-end movie, you might care less about that. If you're shipping a video game that needs to be fast and lightweight, you might care more about that. Okay, so that's motion capture. Now, another technique that we can use is called procedural creation. Where motion capture modeled by hand relies on the artists to create the data, procedural creation rearranges things. It approaches things a little differently. We set up algorithms to model behavior. Okay, so we set up algorithms of what we want to happen, and we push run. I should probably highlight these. And we push run, right? We set up these algorithms and we push run, and we get, hopefully we get the output that we want. A classic one are called flocks or boids, swarms. And I'm going to come back to these actually in a couple of lectures. They're really cool, but the idea is you give each, you create all these agents in a space, you give each one a simple rule, like stay away from your buddy, don't collide with your buddy, but move in the same direction as your buddy. Okay, but don't collide. And then you get these emergent behaviors, it's called emergent behaviors, that actually look really interesting and really organic. So let's take a look at some of these procedural type approaches. So this is a scene from Batman, maybe. There we go. And these bats aren't real, they're procedurally generated. This is a particle system where we're just creating these through an algorithm to make them look the way we want. Now, this is a little old, so if you look at it now, it does look a little cheesy. It looks a little bit out of place compared to what you'd see today, but at the time, it was like, wow, how'd they do that many bats? It was on scene. It was a procedurally generated scene. And the same thing goes for these, where are we? These penguins. There's more bats procedurally generated, and there's some penguins that are procedurally generated as well. There we go. All right, this wasn't drawn by hand. It was created by computer program, and if you look closely, they do look kind of cheesy now, right? It looks kind of like video gamey. It doesn't look real, but this was the early days of procedural work. Another classic example that you might be familiar with is from the original Lion King, the animated one, where the whole scene is beautifully hand-drawn, and you can tell it has that hand-drawn Disney feel to it, which is, you know, a very endearing aesthetic. People quite like it. But then you have this scene, I'm clearly having problems here. Let's try that again. Let's see if I can do something different. Then you have this scene where the antelope stampede, and this was actually created procedurally.
Hey, Uncle Scar. Will I like the surprise?
Simba.
So you can tell this is hand animated because everything jitters a bit, and you have these not quite perfect motions, but exaggerated in an animator's kind of way. And then when the stampede happens, things shift a bit, and if you pay attention, the aesthetic actually changes. Here we go. Now we have these super smooth, realistic looking antelope coming, This is procedurally rendered. This is not hand-drawn. At the time, again, it was really amazing. You had this procedurally rendered computer graphics. People really liked it. Down here, look, again, it doesn't look quite natural. It doesn't match the feel of the rest of the movie. It looks kind of smoothed out and computer game-like. But at the time, it was pretty impressive. And imagine how much time they saved doing this versus an animator drawing every little antelope piece by piece. So that's procedural rendering. Now, let's go back. Cool. Another approach is neural networks or learning. Learning from data. There's a lot of ways, you can take a class on that, right? Machine learning. But, for example, neural networks, hidden Markov models, that kind of stuff. You feed data into a system of what you want and let it generate the output. In both of these, I'll give an example, but first I'll say in both of these systems, the work goes into setup. To setting up all the parameters. That's where the work goes, and then you spend a lot of time tuning and tuning everything to make it look just the way that you want, and then at the end you still have to link all your data to your renderer. Right? You can't just show computer output, it has to be actually rendered objects. You have to link it somehow. And that's a problem that we're actually going to come back to a little bit later. Alright, so I'll quickly show those examples and then we'll be done with this section. So here's the example. We want to move the person to walk around, and traditionally you'd have the model what you want the person to do at every point. You'd have to go, okay, there's a bump, do this, there's not a bump, do that. It becomes hard. But what they did is they recorded data of a person walking over different terrains, and they use that data to teach a system and then generate on the fly reasonable motions over difficult terrain. So these are all generated on the fly using neural networks and getting reasonable results. So this is an example of procedural results where you're not actually solving it, you're not pre-recording it, pre-rendering it, or solving it analytically. Instead, you're actually training a system of how to behave, and then it's behaving appropriately based on the terrain it finds itself surrounded with. Alright, I'll stop it there, and we'll come back and work on to the next part of this unit.